electricity, and gravity all exert forces over a distance. And we talk about how those forces are exerted by fields. So just like you guys had a question on electricity today, where you found that as the distance doubled between two charges, the force got a fourth as strong. Well, that works with magnetism and gravity too. So magnetism is a field force, and it gets weaker as 1 over r squared. Magnetism gets weaker as 1 over r squared, where r is the distance that objects are separated by. Okay? Next up, when we talked about the electric field diagram, what determined if the arrows were pointing out or in? This is another question from the review we just did. Whether protons or electrons, whether it was positive or negative. Well, we don't have positive and negative in magnetism. We have N and S. So the magnetic field lines point out from N and point in towards S. Lines point away from N towards S. Now, the biggest difference between electricity or electric fields and magnetic fields is, could we have something in an electric field that was just a positive charge? Sure, what was it called?
On my arrow pointed towards and away.
Then you drew the wrong arrow from your compass.
I drew the red one.
I'll come look at it in a bit. So the question I'm asking you guys right now is, when we were drawing electric fields, what was just a positive charge called? Say again, Ashlyn? A proton, absolutely. So what would just a negative charge be? An electron, a negative tron. All right. So the biggest difference between electricity and magnetism is that while in electricity we could just have positive and negative, in magnetism you can never have just N and S. It's not possible. Because unlike electricity, where it was a property of the electron, magnetism is more like motion and more like a direction, where when you always have forward, that means you always have backwards too. So magnets, guys, I'm not talking right now, never have just N or S. They always have both. And this is because of something we call domain theory. So I'm just going to grab my magnet, move it down here, and I'm going to retrace it out. So a magnet is composed of a whole bunch of small areas called domains. And each of these domains is basically a emitting magnet. And in order to be a emitting magnet, it's a small group of atoms that have the same electron spin. So a domain is a small piece of a magnet in which all the electrons have the same spin. Have the same spin. I like how Jacob's the scapegoat. All right, so not talking. So in each domain, they have what we call spin. And if they all point in the same direction, or if they all have aligned electron spin, then the net result is that they form one overall magnet. Now, if the domains aren't entirely lined up, they just kind of average a single direction. So in this one, this would be magnetized material. Magnetized. However, if we have a set of domains, again, small regions that are each aligned magnetic spin, however, they are random, well, then they're going to cancel each other out, and they're not going to make a magnet. So here, I would maybe have one that way, one this way, one that way, one this way. Down, up, back, forward. Doesn't really matter. They're all random and canceling each other out. And this would be non-magnetized. All right, and something I forgot to do, I wanted to put quotes around spin. All right, so how do we know this works? Well, we know this works because we can create magnets by giving non-magnetized material a little bit of energy, and when it's got that little bit of energy, we can force the domains, therefore force the electrons, to gain the spin of the other magnetized material around them. So what I've got here is a iron bar and a set of iron channels. And right now this thing is magnetized. So that means that all the domains are pointing in about the same direction. It's not a terribly strong magnet, but it's enough that you can tell it picks up magnetic material. Yes? Okay. So I totally didn't want it to be a magnet, so I'm just going to add some energy and make those domains realign. No longer a magnet. Okay? So, since this is no longer a magnet, that means that the domains are completely random, pointing in all sorts of directions, canceling each other out. If I want to get them to line up, I just have to do this again, but with a little bit more organization. Oh, it gets better. There's going to be sharp sounds. So I'm going to take the magnetic field. There's a strong permanent magnet. No one told me I couldn't. So, now I should have a magnet.
No. Nice to magician.
Oh, don't worry. My explanation that's magic is coming up.
Oh no.
All right. So now all the domains of this section of the iron pole must be aligned in the same direction. They must be aligned in the same direction because I'm showing that it has magnetic properties, meaning that the electron spin is not canceling each other out. Questions about making a permanent magnet? Okay. Now again, I didn't really actually want this thing to be a permanent magnet, so I'm just going to knock the arrangement out of it. I'm not a magnet anymore. Yeah, that would be. Okay. Now, I did that with that bar. I may as well try it with this one. This is a significantly lighter piece of metal. Stick it in here. Clearly not a magnet, right? Nothing sticking to it. So, this is aluminum. It's metal, right? So I'm going to go ahead. Give it the same energy I did like the last one. Well, that's yuck. I don't know. It's something sticking. Bird watching. Okay. Oh, I don't know what it was. I smashed a tick with that hammer. That's not how you smash I had ninth graders. They probably came in on them. Could have been. All right, so a couple things we got here. First of all, we find that you guys talk way too much. Second thing we find is that when we have something that's magnetic, we only find that 3 different elements are magnetic. And those elements are actually found right next to each other on the periodic table. Iron, cobalt, and nickel. Iron, cobalt, and nickel are the only elements that have unpaired electrons with spin. Only elements that can be magnetized. Okay? And we do have a few different ways of magnetizing them. The first one you just saw. I can cause violent vibrations in the presence of a magnetic field, and that will create a permanent magnet. So creating, actually, I want to label this making a magnet. Not to be confused with a certain Netflix series. No, making a murder. All right. So first option, violent vibrations in a magnetic field. Now, the key to the violent vibrations piece was that I was adding kinetic energy. If aside from moving, how else could I add kinetic energy to something? Aside from making it move, how else could I cause something to have kinetic energy in a form? No? You're getting close. You're getting further away. What is, aside from moving, what is another way to have kinetic energy? That's not kinetic energy. Say it. Oh, I heard it. No, temperature. Okay. So, the next way to make a permanent magnet, hey guys, go ahead and put your magnets down for a moment. Okay, is, yeah, I know, right? Extreme heating in the presence of a magnetic field. Extreme heating in a magnetic field. All right, and the last way to make a permanent magnet, guys, not talking. Last way to make a permanent magnet is long durations of time in a magnetic field. In a magnetic field. All right, so if I took some iron and I just placed it in my drawer that has all my magnets and I waited until this time next year, yeah, I would have more permanent magnets. That would do the trick. Looking at these different ways of making a magnet, what do they all have in common? In a magnetic field, absolutely. So when we're trying to make a magnet, there's a problem that seems to arise in terms of trying to understand how you make the first magnet. Because in order to have a magnetic field, you need a magnet. And this kind of winds up being a chicken and the egg question, where which came first, the chicken or the egg? Well, which came first, the magnet or a magnetic field? But where did that field come from? What was causing it? It's the same kind of question. However, this one's got a little bit easier of an answer. Because when we talk about permanent magnets, the first permanent magnets on Earth were actually discovered by the Chinese. The Chinese discovered the first permanent magnets, and they called them lodestones. Basically, they were naturally occurring magnets. Now we know those naturally occurring magnets were created by Earth's magnetic field. So our next topic here is geomagnetism. Ooh, I forgot a part. So when the last person stops talking back there, all right. I kept putting spin in quotes, right? So quick thing on that. About in the early 1900s, when we were learning a little bit about how magnetism works, we said that the electrons had spin. We said this because we recognize that, and I said it earlier, moving electric charge causes magnetism. I said that earlier, right? And that would indicate that anytime you guys created a circuit in the last week and a half, you also created a magnet. So we discovered this, and then we figured, oh, this could probably extend to atoms. And so the atoms must have electrons that have some kind of motion that causes them to be magnets. And we figured, oh, the electrons must be spinning. And as we learned more, we found out, oh, the electrons aren't spinning. They just have a property that makes them magnetic. So we'll call that property spin, because we don't know what else to call it. So when we go back to the daily question, what makes something a magnet? We could say the spin of an electron. If you ask me then, well, what about an electron is it? My answer would be magic, because we really don't know. We really don't know what about an electron other than its spin, which we just kind of made up a word. We don't really know what about the electron causes magnetism. So we know it's something to do with them, but we don't know what about them. All right. Questions on that? Good, then I'm coming back to geomagnetism. All right, so when we draw out the Earth, we've got Earth here, we've got the North up here, we've got the South down here, and we've got magnetic field lines that flow from one spot to the next, out of the South and into the North. Now, some of you had issues with your magnets, and I'm betting at least a few of you it's because when you took your compass and you figured out which part pointed north, you took it and you said, well, that's got to point at an end magnetic pole. It should point at the end side of your compass because it points north. Well, what part of one magnet is attracted to the end pole of a different magnet? The opposite. So that would be the S pole, right? So if I take a compass and the end pole of my compass points that way, what's got to be over there? A south or an S pole. So if I'm pointing to geographic north and the end pole of my compass is pointing to geographic north, what's got to be at geographic north? A magnetic south. Yeah. So I'm going to go one more time. Take your compass. Your compass points that way. That means that this side of your compass that points that way is a magnetic end pole. Okay? We're good? Magnetic end pole points that way. You guys know that opposite poles attract. So in order for the end pole to point that way, the opposite pole's got to be up there somewhere. So what's got to be over there? An S pole, because it's the opposite of what's pointing towards. A magnetic end pole. Now, you'll also notice that I keep avoiding using the words north and south for the poles of the magnet. I do that because north and south, to me, talk about geography. If I say that way and I say north, I'm talking about going that way towards the North Pole in geography. If I say S pole, I'm now talking about magnetism. But because that's an S magnetic pole, but a north geographic pole. So on our globe here, no. That's just left and right when facing north. Okay, so magnetic poles on Earth are opposite from the geographic poles. Magnetic poles on Earth are opposite. Are you bringing it close to a speaker or something? Oh, that's awful. Don't do it. Are opposite the geographic poles. All right. Now, we still run into the same problem. Okay, well, where'd Earth's magnetic field come from? Earth is not a permanent magnet. Earth is an electromagnet. like the circuits you guys have been playing with for the last week and a half. So Earth gets its magnetism from electricity that's being conducted within it. Set them down. All right. So let's take a look at the planet for just a second. What's the outermost layer of Earth? Crust. Okay, good. That's boring. Let's get rid of that. Next layer inside. What's the next layer of the Earth? Mantle. Good. Now we found the fun part. Mantle, and at the very center, core. So Earth gets its magnetism from material in the outer core and the innermost section of the mantle. Because the material there is hot magma, and magma being hot has lost some electrons and is moving charge. Moving charge causes magnetic fields like Earth's. Okay, so magma convecting. What is convecting? We did. Say again? When what rises? When heat rises, we get convection. So it's like a boiling pot of water. The hot stuff rises, the cold stuff falls. Well, magma in the Earth's center does that too. The hottest magma rises, the coldest stuff falls. So magma convecting in Earth's outer core, so core and mantle, moves charge. Moving charge causes a magnetic field. Moving charge causes a magnetic field. Okay. With that piece of information, we can now actually talk a little bit about not just our planet, but other ones. Earth is not the only planet with a magnetic field. Mars also has a decent magnetic field. And actually, the magnetic field is incredibly important to life on Earth. Without the magnetic field, life on Earth couldn't exist. It couldn't exist because the magnetic field protects us from X-rays and gamma rays coming from the sun. Why do we care about that? Because they cause cancer at the very least, right? If Earth were to be bathed by all of the sun's gamma and X-rays all the time, life would never have come to exist. It would be destroyed before it could have even started. So Earth's magnetic field is incredibly important to life on Earth. And this is where I get to give you all sorts of gloom and doom. So if you take something hot, like a baked potato, I don't know why a baked potato came to mind. Okay, you got a baked potato. And you've got a second one of different size. You've got a larger one and you got a smaller one. Which one's going to cool down first? Smaller one, all right. But over time, both of them will cool, right? Well, as either one cools, as Earth cools, we get less convection. Why is that a problem? Less convection means less magnetic field. Less magnetic field means more gamma and X-rays. Earth is cooling currently, and therefore we're getting weaker magnetic fields. We're getting more gammas and X-rays, and that's not a good thing. You know why. Now, it's not. It's really not. Couple other things. Shh, stop talking. Few things there. First of all, we've seen this actually play out already. Just like the larger potato, smaller potato idea, where the larger potato retains heat for longer and the smaller one cools down. Mars is our version of the smaller potato. Mars is smaller than Earth and therefore has cooled faster. Because Mars has cooled faster, its magnetic field is weaker, and more gamma and X-rays make it to Mars's surface. Therefore, life can't develop on Mars's surface. Could it have at a previous time? Possibly, because it had more magnetic field, therefore less gamma and X-rays, more atmosphere, and a good chance that life could have developed there. However, because it's smaller, colder, less magnetic field, more gamma and X-rays, that's not good. In our favor, the rate at which Earth is cooling is about the same rate at which the sun is going to die. So we've got a few billion years. We don't have to worry about it. But what we do have to worry about and it could literally happen any time because we're overdue for it by about 1,000,000 years, is that Earth's magnetic field hasn't always been oriented like this. Studies of the Earth's the seafloor have shown us that over the periods of time of tens of millions of years, Earth's magnetic field flips. So when we say that the S pole is here and the N pole is here, that hasn't always been true. In fact, it changes every few 10 million years. So even within the history of, since the time of the dinosaurs, Earth's magnetic field has flipped a few times. It could start, actually, some studies have shown that it may actually be starting now. Now, the next question, hey guys, you need to be quiet so I can answer, the next question is, well, why do we care? Okay, first of all, more fundamentally, certain animals use the Earth's magnetic field for navigation. Migratory animals, such as birds, and some, I believe, dolphins and whales might. And also possibly certain fish. I'm not 100% on that. But certain animals use the magnetic field for migration purposes. So, I don't compete. You're competing with me. The next issue there is that we don't know how long it takes. It may be a very slow process, so they can naturally adapt to it. I mean, they exist, so it must be something that's very slow. The other thing is we don't know how it affects us. We know it'll flip compasses. Great, compasses will point in a different direction. But changing magnetic fields also creates current. And we've never had electrical lines before. So depending on how fast Earth's magnetic field changes, we don't know how that influences electrical grids. We already know that things like solar flares, which create massive magnetic fields, can knock out power grids on Earth. We've seen it happen. We don't know how a changing magnetic field here on Earth is really going to influence us either, because we've never seen it happen. Probably. All right. That's the entirety of the notes for today.